Hello everyone, thank you for joining me today. I'm excited to delve into a topic that sits at the intersection of computer graphics, machine learning, and data visualization. The topic of today's talk is interactive volume visualization via multi-resolution hash encoding-based neural representation. During today's presentation, we will first explore the motivation and background behind our research, setting the context for the problem we aim to address. We will then transition into an in-depth analysis of the neural network architecture that serves as the backbone of our technique. Following that, we'll delve deeply into the training and rendering processes that bring our visualizations to life. We will conclude the presentation with a discussion on future research directions. In our research, our primary emphasis is on the volumetric field. For those who may need a refresher, a 3D volumetric field is a function that maps three-dimensional coordinates to specific data values. These fields have widespread applications and are integral to various domains, including scientific simulations, medical imaging, and advanced computer graphics in production settings. Volumetric fields are traditionally stored using discrete representations. This involves tessellating the space covered by the volume with 3D primitives and then sampling the volume at either the primitive vertex positions or their centers. When this space is uniformly tessellated using 3D rectangles, we obtain grid representations. While these are straightforward to access, they can be memory-intensive, especially at higher grid resolutions. For fields with significant spatial variations, an unstructured representation can be more efficient, allocating higher resolution to areas of interest. These representations tend to be more compact, but accessing values can be intricate due to the complexity of the data structure. Another approach to mitigate memory usage is compression. However, this introduces its own challenges. Accessing values from compressed data necessitates decompression, adding latency, and potentially increasing the memory footprint once again. Our objective is to identify a data representation that seamlessly combines simplicity, compactness, and ease of access. Our solution leverages the capabilities of neural networks, specifically implicit neural networks, to address these challenges. An implicit neural network approximates a given volumetric field by mapping 3D coordinates to data values. We train this network using coordinate value pairs sampled from the original volumetric field. The trained network weights then serve as our compressed representation, allowing for direct data access through inferencing. In terms of architecture, a typical implicit neural network begins by transforming an input coordinate into a high-dimensional feature vector, a process commonly known as position encoding. This encoded feature vector is then processed through a MLP unit. MLP units can be implemented using various architectures, such as fully connected neural networks or ResNet-based networks with sign activation functions. In our research, we opted for a fully connected neural network for the MLP unit, as its sign rigizes well with the position encoding method we employ. When it comes to position encoding, there are a multitude of approaches to consider. Earlier methods often relied on sine and cosine functions to encode input scalar values, but these techniques had limitations in terms of quality. A more recent advancement involves the use of additional data structures, such as multi-resolution grids, to store trainable parameters in the encoding layer. Each vertex in these grids stores a set of n trainable parameters, often referred to as features. Here's how the encoding process works. Given an input coordinate, x, y, z, we first query the corresponding grid cell at the initial resolution level. We then extract the feature vectors stored at the vertices of this cell and perform trilinear interpolation. This yields a small vector of size n for the first resolution. We repeat this process for each subsequent resolution, concatenating all the smaller vectors to form a larger vector of size m times n. This larger vector serves as the encoded feature vector. This approach, commonly referred to as grid-based encoding or latent grid, significantly enhances the quality of results and permits the use of very small MLPs, thereby also substantially improving training and inference performance. However, the method can become memory-intensive, particularly with increasing grid resolution. To tackle the memory-intensive challenge of grid-based encoding, a novel method has been introduced. Instead of storing features in a traditional 3D array, this approach utilizes a hash table to house these features. Intriguingly, the method intentionally avoids resolving hash collisions. As a result, multiple grid vertices from the same resolution could map to an identical feature vector. This intentional overlap leads to a substantial reduction in memory usage. We found this method is also very effective for scientific data. This brings us to the contributions of our work. First, we pioneer the application of multi-resolution hash grid encoding to scientific datasets. Building on this, we've engineered a highly optimized training pipeline capable of accommodating diverse types of data. Beyond that, we've developed specialized acceleration structures and innovative rendering algorithms, enabling the direct rendering of the trained neural representation with advanced illumination effects. Lastly, we've ventured into the realm of online training, assessing its feasibility for real-time applications. Now, with the foundation laid, let's delve deeper into the intricacies of our training process and understand how it brings our innovations to life. To train a neural representation for volumetric data, our process is threefold. First, we generate random coordinates uniformly within the domain of interest. Next, we sample these coordinates using the ground truth volume to obtain coordinate value pairs. These pairs then serve as the training data to optimize our neural network. To expedite this process, we've taken two key steps. First, we've implemented our algorithms using low-level programming languages like C++, ISPC, and CUDA to maximize efficiency. Second, we've leveraged hardware acceleration technologies, such as tensor cores, wherever possible. The result of these optimizations is great. We achieve up to a 35 times increase in performance speed compared to a standard PyTorch implementation. Our training approach is also designed to be versatile, adapting to different data sizes and memory constraints. For data that fits within GPU memory, we load it directly onto the GPU and leverage hardware-accelerated interpolation for optimal performance. When dealing with data that fits within system memory but exceeds GPU limitations, we load it into system memory. Here, we employ multithreading and SIMD to accelerate interpolation and utilize OpenVKL to sample unstructured volumes efficiently. For large-scale data that surpasses both GPU and system memory, we've implemented out-of-core streaming techniques to manage the computational load effectively. Our streaming implementation offers a 10 times speed advantage over simple virtual memory mapping, and enables us to train on terascale datasets using just a single GPU. To summarize our training outcomes, for the first 9 datasets, which comfortably fit within a single GPU, we achieved rapid training times ranging from just 10 to 40 seconds. For larger datasets, the performance was primarily bottlenecked by CPU and I/O limitations. Importantly, across all datasets, we were able to achieve impressive PSNR values and outperform the other related work. When we turn our attention to the rendered images, the conclusions are consistent with our training results. Rendering directly from neural representations yields images that are visually nearly indistinguishable from the ground truth. Further, when we assess image structure dissimilarities through visualization techniques, our method continues to outperform related work in the field. After examining our training results, let's transition our attention to the rendering techniques we have implemented. To render neural representations interactively, specialized renderers are essential. We have developed 2 such renderers, each based on different principles. For instance, one approach allows the neural network to be directly inferred within shader programs. This necessitates a customized CUDA inference kernel and generally aligns with the megakernel paradigm commonly used in interactive ray tracing. While enabling hardware acceleration does require some low-level synchronization, it doesn't fundamentally alter the rendering algorithm. Therefore, this method is particularly well suited for more complex rendering algorithms. This small diagram provides a high-level overview of how in-shader rendering operates. In parallel to the in-shader approach, we've also developed a renderer based on the wavefront style, which we refer to as the sample streaming method. In this method, sample coordinates are directly streamed from the kernel to the GPU's global memory, with the network inference being carried out explicitly. Given that volume rendering algorithms necessitate multiple volume samples per render pass, we implement stream compaction to eliminate early exited rays. Though this style provides versatility in adapting to diverse network structures, it requires a redesign of the rendering algorithms itself. In our work, we developed the algorithms for 3 distinct volume rendering styles: ray marching with single-shot heuristic shadows, and volumetric path tracing. The algorithms for ray marching and single-shot shadows are relatively straightforward. In the subsequent slide, we will delve deeper into path tracing. For volumetric path tracing with direct lighting, the complexity increases substantially. This is because path tracing requires stochastic estimation of travel distance, and the estimation result for the next sample is closely tied to the neural network value at the previous sample position. The complexity is further compounded when multiple types of rays are involved. We discovered that the key to successful implementation lies in maintaining just one ray object per thread and registering its status in the global memory. This allows for active role switching of the ray object when needed. These are the results we have obtained thus far. It's evident that our rendering algorithms generally outperform the current state of the art in terms of performance. However, they still fall short of the level required for seamless interactive visualization. To enhance the rendering performance, we investigated deeper into exploring additional acceleration structures for rendering. For instance, we can establish macrocells over the volume domain. A macrocell is fundamentally a large cell encompassing n-cube voxels. Within each macrocell, we can store the minimum and maximum voxel values, as well as the maximum opacity with respect to the current TFN. Utilizing macrocells allows us to implement empty space skipping and adaptive sampling. We can also expedite volumetric path tracing by establishing varying majorant bounds. Given that the macrocell acceleration structure aims to minimize the frequency of volume sampling, we found it particularly apt for rendering neural representations. With the incorporation of macrocells into our methodology, we've successfully attained interactive rendering performance, witnessing a performance boost of up to 40 times. When comparing the two rendering styles in our implementation, sample streaming proves to be approximately 3 to 8 times faster than the in-shader method. Why sample streaming is faster? It is because our network input encoding method can be executed in parallel. This parallel execution leverages increased data throughputs. As a result, we're able to interactively path trace even datasets on the terascale. Interestingly, we discovered that the training process is quite efficient, taking only about 1 millisecond per step. This speed allows us to incorporate a training step within the rendering loop, thereby achieving online training. Let's take a look at a demo to see this in action. In the demo showcased, we're kickstarting the training of a neural network from a random initialization while also rendering it in real time. As you can see, the neural network quickly converges to the underlying volume data, all within the span of a single visualization session. Now, let's cast an eye toward future work. Looking forward, we believe this direction is still in its early stages, and many interesting topics remain unexplored. For instance, how can we effectively handle distributed data? What are the implications and potential applications for time-varying and ensemble data? Is it feasible to apply the Gaussian splatting technique to address similar challenges? And many more. This concludes my presentation. Thank you very much for your attention. This research was also supported in part by the Department of Energy and Intel One API Centers of Excellence. I'd also like to thank our collaborators for providing us with valuable datasets.